So I remind everyone that what we are doing is trying to get the electric field for a point source, so at a distance r away from this source. Okay. So what we have done so far, we arrived at this position here. So I defined my Gaussian surface such that theta is equal to unity, cosine theta is equal to unity everywhere. So I'm going to have EDA. Okay. And what I'm going to say is that I'm by symmetry, by spherical symmetry, I'm going to assume that my electric field is constant at all angles at this distance r. So basically what I'm saying is that the electric field at this position here, okay, is equal at this position here, at this position here, at this position here, at this position here. Anywhere I am, because I am a distance r, there is no real reason why the electric field at this position would be greater or smaller at that position, okay? Especially that my Gaussian surface that I have chosen is centered on the charge. So consequently, r is an equidistance. So it's everywhere, it has an equidistance from the charge, okay? So for this reason, what we can say is that, my E is constant at R and E is not constant. I'll come back to that. So E is not constant. So if you are solving the problem and I'm correcting and you tell me that E is constant, you will have, you will not get the full grade, okay? And the reason is that E is not constant, but E is constant at R, okay? So if R changes, E changes, and we will see that, okay? But because the integration is basically now only on the angle, then this electric field is constant at this distance, okay, by symmetry, okay? So if then it's constant, then if it's constant, it gets out of the integral, and I'm left with E integral of the A of a Gaussian surface, and this is the area of my Gaussian surface. What's the area of my Gaussian surface? It's a sphere, so it's equal to 4 pi r squared, okay? Because r is the radius of my Gaussian surface. Okay, now let's continue with solving the problem. Now what we need to do, we need to solve the left-hand side. Okay, what's the left-hand side? It's Q inside the Gaussian surface divided by epsilon 0. What's the charge inside the Gaussian surface? The charge inside the Gaussian surface is equal to the charge. There's only one. Okay, and so my Qn is simply equal to Q. Okay, let's put everybody together and solve the problem. Okay, so what do I have? The integral will give me E multiplied by 4 pi r squared, and the right-hand side of the equation will give me Q divided by epsilon 0. Consequently, my E will be 1 over 4 pi epsilon 0 Q over Q over r squared. And now I actually have the expression of the Coulomb's constant. The Coulomb constant was obtained by Coulomb experimentally. It has now a significance, has now not only a value, but also a significance. It really reflects epsilon 0, it's 1 over 4 pi epsilon 0. It really affects the way the space react to the charge, okay? Because that's what I said epsilon 0 is, okay? So this is now, and notice now what I have from the application of Gauss's law. What I have is the amplitude of the electric field. Okay, why? The direction I already have it. It's a sphere. Consequently, the electric field is always perpendicular to this sphere. Okay. Any questions? So this is usually, it would have been given a problem in the exam. Okay. Okay. So this is problem number 1. That is, we obtained the electric field at the surface away from a point source. Let's consider now an insulating sphere. So find an inside and insulating charge sphere with find electric field inside and inside. So basically at R smaller than A. Okay. Now I have not had the time to solve it, but let me walk you through this. Okay. So this, we start. We start here. So my phi e is equal. Let's once again. I would like to use. I want to have the electric field of a charge. Then what I'm going to do is I'm going to use Gauss's law, which stands for phi e equal to integration of the closed surface, which is the Gauss surface of E squared A equal to charge inside divided by epsilon t. Okay. So now what I want is I want to describe. I want to I want to. Are you able to see? All right. Okay. What I'm going to do, I'm going to now go back again and come up with these. So basically, this is basically one. Step one. Okay. One is to recognize that you must use the Gauss's law. Okay. What we said, two is to define what Gauss's law. So what we say is the same thing. The Gauss's surface is a sphere. Also, we're going to take into advantage. We take advantage of the spherical shape to define the Gauss's surface, which is a sphere centered at O with radius R smaller than A. Okay, that's your starting. Okay, my first point is really to define what my Gaussian surface is. Okay, okay, this is one. Okay, and what is O? This is my O is the center here of my sphere. Okay. Okay, so this is number two. Third point is, of course, what we need to do is solve the integral. So what do we have? We have integral of E scalar dA. We have one that theta is equal to 0 everywhere on the Gaussian surface. On the GS. Why? Because if I now, let's say, take here, this is the element area A, and if I have the electric field, that's going to be also my electric field. Okay, so they are both parallel, okay, because they are both radial. They are both going radially. Okay, the sphere has element dA, and the electric field also has element dA. So if theta is 0 everywhere, this means that cosine theta is equal to unity everywhere on the Gaussian surface. Okay, so this is basically one. All right. I hope that you guys are able to follow. Okay. So second point is that what we said. So basically now the integral. I usually write integral like this, integral over the Gaussian surface explain theta is equal to 0, please. Yes, come on, give me a second. Yes. So what we said, if I have a sphere, okay, if I have a sphere, the electric field is radial only, right? So consequently, the electric field is let's say is like this. okay? Or like that. Sorry. Or like this, radial. It's only in the radial direction, okay? Now my Gaussian surface is centered on the same point. That is, if I now account for the element area, then the element area is in this direction. Here. If I account for it here, it will be in that direction, right? Because it's perpendicular to the surface, okay? If I account for it here, then it will have to be in this direction as well, okay? So at any point, theta is equal to 0, at any point, okay? And so the integral of E dA cosine theta is simply now equal to integral over my Gaussian surface of E dA, okay? And now I can reuse the issue of symmetry. So now I can say, because of symmetry, okay, E is constant at R, okay? We said that the Gaussian surface is a sphere centered at O with radius R, so at R, E is constant, and E is not constant. E is not constant, but E is constant at a distance R. Okay, basically what it means is that what it means is that E does not depend on the angle, because the only thing which is changing is the angle. So it does not depend where you are on the sphere, okay, on the angle, whether it's 0 degrees, pi over 2, pi, 2 pi, etc. Okay, it does not depend. So what this means is that integral, since it is a constant over my Gaussian surface, okay, of E dA is now the same as before, is equal to E integral over Gaussian surface of dA, which is equal to which is equal to E multiplied by the area of my Gaussian surface. Okay, what's the area of my Gaussian surface? It's a sphere, so this is equal to E multiplied by 4 pi R squared. Okay, now we come to the fourth point, okay, which is Q inside. So let me first get rid of these. I hope that this is clear for you why electric field is and the A are always parallel in the way we have chosen it. Okay. This is why the choice of the the Gaussian surface is very important, because it's gonna, if you have chosen, for example, if you have chosen to have a sphere not centered, so basically I'm gonna go here. Let's assume I'm gonna choose a sphere which is, let's say, like this. Okay. Okay. Let's assume this is my Gaussian surface. In this case, what I want to do is I want to integrate of the electric field. So basically, what this means is that sometimes I'm going to have the electric field here. Okay. Sometimes I'm going to have it here. And sometimes I'm going to have it here. And sometimes I'm going to have it here. And so these electric fields at these green dots, there's nothing which can tell me that they are the same. So I cannot get out of the equation. Okay, everyone? So it cannot get out of the equation. The only way I can get out of the equation is I center it and I make a spherical object such that now theta is equal to 0 everywhere and E is constant at the distance R away from the center. Okay? So basically now, this is why the choice of the Gauss surface is extremely important. Usually, often it is intuitive, but nevertheless, it's extremely important. Now we need to go to the right-hand side of the equation. Okay, what's the right-hand side of the equation? I have Qn, Q, the charge inside my Gauss. Okay, what is the charge inside my Gauss surface? Okay, let me go back here. This is my Gauss surface here. Okay. Gotta remove these guys. I hope you understood why the choice is very important. Okay, so let me make this in let's say in green and make it transparent a little bit just to make sure that you see what's happening. So this is my Gauss surface, right? So what's the charge inside? Well, the charge inside is really what's inside this green area. That because, as it says, it's inside the Gaussian surface. So definitely it is not the total charge, but it is a partial part of the charge. And remember, when I was in chapter 1, I told you when you need to use a partial, when you want to know the partial charge for a partial volume, you use the charge densities. And so what we said, this is now volumetric charge density. So to obtain Qn, we use the volumetric charge density, okay, rho, which is equal to Q, total Q, divided by the total volume as well. Q is equal to total Q divided by the total volume. Or it can be the partial Q divided by the partial volume. So rho is this equal to, it's equal to Qn, Q inside the Gaussian surface, divided by volume of my Gaussian surface. You understand this point? Okay. Okay. So now I can solve this issue. So what do I have? I'm going to have my Qn, which I want, is equal to, I have the initial charge and I have the radius A. So basically I have Q divided by 4/3 pi A Q multiplied by the volume of the Gaussian surface multiplied Q multiplied by 4/3 pi R. That's the volume of my sphere with radius R. Okay. Initially, my total charge with radius A has subtotal charge Q. Consequently, I have the partial charge, which is the charge inside my Gaussian surface, as equal to the total charge divided by equal to the 4 pi R squared, the volume of the Gaussian surface, divided by the volume of my total volume. Okay, so this is giving me this equal to Q, total Q. Okay, R to the power 3 divided by A to the power. Okay, so now we have all this. Let's solve. So 5, solve and answer the question. That is now, on what do I have on the right hand side? I have E multiplied by 4 pi R squared equal to the charge inside, which is Q, that I know, I've given it to you, R to the power 3 divided by A to the power power 3. And then, of course, this is all divided by epsilon 0. Okay? So what this gives me now, I put the electric field. So my electric field E is equal to 1 over 4 pi epsilon 0 multiplied by capital Q, multiplied, I have R squared and R multiplied by R divided by A to the power 3. That is my solution. Okay, guys? You understand? Okay, so now we have the electric field inside the sphere. We can have the electric field outside the sphere, which is here, E equal to 1 over 4 pi epsilon Q over R squared. Okay, one interesting problem is that check what happens at R equal to A. Okay, so from R equal to A, okay, using, let me see what do I have here. Okay, so outside you do the same as I said. So we have Q over KEQ over R squared. So at R equal to A, what do we have? So at R smaller than A, okay, we had E. This is the value of E. Check. So Control C. So this is the value of E. Okay. So this is at R smaller than A. Now at R greater than A, what do I have? I have as a point source that is E equal to 1 over 4 pi epsilon 0 Q over R squared. That's what we have. So let's see what happens at R equal to A. Okay, let me take the case here. So using this formula, the one inside at R equal to A, what do I have? I have E equal to 1 over 4 pi epsilon 0 Q. Okay, now R equal to A, so I'm going to have A in the numerator and A to the power cube in the denominator. So basically, this gives me A to the power 2. Right? So this is my first answer. Okay. Now, what happens if I use the second formula at R greater than A? Well, all what you need to do is put instead of R A, and I'm left with exactly the same equation. So what happens is that when you have, so globally for a sphere, okay, at R smaller than A, the electric field increases linearly with R until a certain point, which is the surface. And then above the surface, outside the surface, the electric field will decrease as 1 over R squared. And what we say here is that this really demonstrates that whether you solve from outside or from inside, at the surface, it's the same electric field, okay? Which is 1 over 4 pi epsilon 0 Q divided by A squared. Now, the reason why it increases linearly with radius is that the bigger is R, the more you have charges inside the Gaussian surface, okay? And so consequently, the more the electric field is stronger, okay? Until it reaches the maximum value. And then from this maximum value, it then decreases with 1 over R squared, okay? Now, here's another problem, okay? Guys, if you have questions, please unmute yourself and ask, okay? Don't hesitate at all, okay? So assume that I have a thin spherical shell, like this one. So a shell is basically like an egg, for example, okay? It's a shell. On the inside, there's nothing, and on the outside, there's nothing as well, okay? There's nothing, all right? And there's only charge on the shell. The question that I ask you here is, what's the electric field at R smaller than A? So basically inside this shell, okay? And the way to answer this question is, of course, using Gauss's law. What does Gauss's law tells you? It tells you the integral of E scalar dA over a Gaussian surface. Let me take this one here. Let's see a second. Okay. So it tells me, using Gaussian, that's my Gaussian surface, E integration of Gaussian surface of Q inside divided by 0. So what happens for R smaller than A? Okay, what do? We choose a Gaussian surface. GS is a sphere, once again, centered at O. I will tell you in a second what is O, the same center of the whole spherical shell, with radius R smaller than A. Okay? Okay, I hope this is all clear. Okay? Just to be able to. So what now? Let's apply Gauss's law. So integral phi E, the integral now is equal to how much? Control C, Control V. Okay, now what's equal to? What's the, now in this case, let me do that. So with radius O, so O is here, okay? O basically is here, and that's the center. Okay. With radius R. In this case, what's the charge inside? Q inside is equal to how much? If I have my sphere, this is my Gaussian surface. That's my Gaussian surface, Maslow. And this is my Gaussian surface here. My Gaussian sphere. Okay, that's what I said. For R smaller than A, Gaussian sphere centered at O, there is R smaller than A. What's Q inside in this case? Q inside this case is equal to 0. There's no charge inside. Okay? Since the sphere is something that cannot be equal to 0, so this tells me that my electric field is equal to 0. I don't have electric field inside, even though I have a charge. Okay? But I don't have electric field inside. Once again, one can think of it in terms of electric field lines. So electric field lines going in is exactly like the fields are going out. So basically, there is no net electric flux, and consequently, my electric field is equal to 0. Okay, now what happens for R greater than A? Okay, again, we choose a sphere with radius R greater than A. And now I solve exactly what we did before. That is, I choose the Gaussian surface. So I chose the Gaussian surface, and consequently here, the right-hand side will be E multiplied by 4 pi R squared. And then the E multiplied by 4 pi R squared equal, what's the charge inside? Is equal to Q divided by epsilon 0. And consequently, my E is equal to 1 over KE, if you want, which is 1 over 4 pi epsilon 0, Q divided by R squared. So basically what you see is that almost independently of the shape, once you are outside, the electric field is the same, whether it is a point source, whether it is a sphere with some radius R, or it is a hollow sphere, it's exactly the same thing. At the end of the day, that's the electric field. Okay? Fine. What time? I'm gonna stop here, and I'm going to ask you guys as a homework, okay, to solve these additional problems, okay, to demonstrate until here. So basically these two problems, please solve them on a sheet of paper, make a PDF document, and send them to me if you want, just to double check that you understood correctly what I said during this lecture. Okay, let me see. Participants, questions? Which two? This one here. So it's 13 and 14. Okay, 13. So find the electric field at distance r from the axis. Basically, you will have to show that it's equal to 2ke lambda over r. And the one is that you have an infinitely thin sheet and get the electric field outside this sheet. Please do it as I did it here. Okay, on 2 sheets of paper. Picture them, make one PDF. There's a Genius scan, you know, Genius scan. I'm gonna write this to you. Genius scan, it's an application, okay, where it can transform the picture into PDF document and send them to me by email. So you have these two homeworks here, okay, that you need to do by tomorrow.